Welcome back. In the last lecture, we looked at the ledger. Now, we've seen that there are issues certifying if somebody actually made a transaction. Because of this, what we need to add to the system is a way of certifying a transaction. And we do this through public keys, secret keys, and what we call digital signatures. Now, if you do a transaction and you want to sign, like you sign throughout your life with a pen and paper, online is a bit different, right? Because you don't just want to sign something, take a picture of your signature, because anybody can forge that. Anybody can take a picture of it and say, I am this person, this is my signature. We need to create what we call a digital signature. So digital signature is the process of guaranteeing that the content of a message have not been altered in transit, that you actually wrote this transaction or this message, right? Now, how do we do that? We do that by generating a public and private key, okay? We sometimes call it public and secret key, and we use these to encrypt and decrypt information, okay? A public key is something that is available to everybody. A private key is a key that you keep to yourselves, right? You don't show to anybody. And they're not actual physical keys. They're actually pieces of code, okay? But that's what we call them. So you get two pieces of code. One is public, one is private. The public you can give anybody. The private you keep to yourself because you use that to sign whatever you want to sign, right? So the way it works is basically like this. You have a public key and a secret key. And the reason why we call it secret is because we usually write PK for public key and SK for the secret key. So you have these two keys. Then there's two functions that are generated for you, okay? Now, we can go super deep into digital signatures and we can have hours and hours worth of courses on going into the technicalities, but we don't want to do that in this course, right? What we need to understand is there's a function. And this function, what it does is it takes your information. That information could be a transaction. You can say, I'm transferring $5 to Omid. And that's the information. You do the hash of that information. You put it in here. You put in your secret key as well. And the function is going to return your signature. And that's it. Voila. You have a signature. You've signed the transaction. Now, if somebody came in and changed that information, well, guess what? He wouldn't get the same signature. And he would need your secret key. And nobody has your secret key, so nobody can forge your signature. Now, when somebody else sees your signature, how can he know? Because the signature is, again, a series of code. How can he know this is actually your signature? How would he know that? Well, there's something that's called the validation function. And the validation function actually takes in three variables. It takes in one, the hash of the information. So again, if I send $5 to Omid, we do the hash of that. It takes in the signature that you've just provided, that we see on the ledger, and it takes that in, and it takes your public key. It takes all this information and it returns true or false. If it returns true, it means this, in fact, is a true transaction, is a true signature made by you, right? We have your signature, we have your public key, and we have that transaction. And by putting all that in the function, it tells us it is true that it's you. Now, if somebody altered your information, well, you know what? The hash of that info is going to be different because, as we've seen, hashes of something that is different will be different. So then it would return false. If it's not your public key, and it's somebody else's, it would return false. If it's not your signature that was generated by you, it would return false as well. And if this was a signature that you've done on another transaction which had different information, and somebody tried to forge it by copying it and put it on a different transaction, it would also return false because it looks at that information as well. So this process actually certifies that nobody can lie about a transaction on the ledger, right? If we go back to the example we've just seen, when I am doing this transaction here, let's get back to this. When I'm doing this transaction, let's say I'm sending Cam $20. What I do is I take the hash of this, right? I apply my my secret key on it that nobody knows, and it returns me, it returns my signature. This might be my signature, right? Now, if somebody else wants to certify that this is my signature, well, he has the validation function. He goes in and he looks at my signature, he looks at the hash of this information as well. So he gets that as well. And he sees my public key. So public key, I give it to everybody. Everybody knows what my public key is. It's my address, right? And he has my public key. He takes all of that information in 1, 2, 3, and it returns, this validation function is going to return true or false. In this case, since everything is true, it will return true. And he will know that I signed this. If somebody else, like let's say somebody like Omid who wanted to steal my money and say, oh, Mo sent me $75, he cannot sign it because he doesn't know what my secret key is. So whatever signature he ends up having or forging, or you know what, maybe he's a bit smart and he's like, you know what, I don't know his secret key, but I know that he signed this. If he tries to use the same signature that I have used previously, it's not going to work. Why? Because this signature also used the transaction, and this transaction is different than this transaction, right? And since this transaction is different than this transaction, when he puts it in the validation function, right, the hash of this is going to be different than the hash of that. So even though my public key is the same, then if he uses that signature and this hash, it's going to return something completely different. So this is not correct. So nobody can forge a signature because the signature requires the secret key. And they can't even use a signature that was used before because every single signature is derived by using that transaction. So unless the other transaction is exactly the same, he cannot copy that. And even if there was another transaction that was exactly the same, like Mo sends Cam $20, well, you know what? On the ledger, we have a small number here, like 1, 2, 3, 4, that we add to it. So this might be 4, this might be the 5th transaction. So even if it's the same, there's a little number that's different. So it's actually never the same. The message is never the same. So we can eliminate the risk or eliminate somebody being able to forge a signature. It's impossible to forge a signature. And thus, we don't need to trust the actors. We don't need to trust the people, right? Because we trust the protocol. We trust the system, and mathematically it works, right? And you can dig deep into cryptographic hash functions and to digital signatures, and they are robust. It's impossible to break unless XYZ, but the probabilities are almost non-existent, right? So because of that, digital signatures certify the trust we have in these ledgers, right? Now, there's other problems. Even if we do certify these transactions, well, you know what? What happens when the population grows? And now there's more people. There's Cam, Mo, Omid, Queenie. But now, as with Bitcoin, right, there's a bunch more people, right? Albert came in, and Joe came in, and Nick, and Nancy, and thousands of people. And this ledger, everybody has to have a copy of it at the same time, right? Everybody can read from it, everybody can write to it, but it's also distributed. It's a distributed ledger, meaning that everybody always has it and everybody can put transactions on it. Now, the problem with that is what happens when you have millions of people using it, right? And it's distributed, and somebody, let's say in Montreal, wants to send somebody $20, and somebody else, in Australia wants to give somebody else $20. And everybody in different locations are doing transactions. There's latency and delays in time, right? And who has which copy of the ledger? Because everybody has a copy of this ledger. Everybody has it there. But what happens when somebody here makes a transaction and he sent this transaction everywhere so everybody knows that it happened, but somebody else had another transaction happen that's different than here, and then people have different copies of this ledger? Then which one is true, right? What is the truth? Which one do we believe in? And what happens if, Mo, Omid says here, he tries to trick people by saying Mo sent me $75 and he forges the signature. Who's responsible for making sure that these signatures are correct? Who verifies that? And, who verified that this actually is the right ledger and it's not a different ledger that's somewhere else, right? So there are still these issues. What we need is a way to have consensus, right? And consensus is basically everybody agreeing on what is the right ledger and using that one for their transactions and distributing it to everybody else. And this is, what the blockchain is going to do by building on top of the ledger system and on top of the hashing functions and the secret key public keys for digital signatures and creating this distributed ledger that has consensus on what is the truth. And this is what we're going to see in the next lecture.